Hey everyone, welcome to my FPGA design series. I'm Dr. Engineering. Today we will start with a question. Have you ever wondered why FPGAs can perform calculations faster than traditional calculators? Well, the secret lies in their ability to handle complex arithmetic operations in parallel. As we discussed in the full adder tutorial, all processes in FPGA run simultaneously once power is supplied, unlike software programming languages like C, where each statement runs sequentially. This means only when the previous sentence is finished, will the next sentence in C program will begin. So the FPGA runs faster than the traditional calculators. In today's video, we're going to dive into one of these operations, a ripple carry adder. By the end of this tutorial, you'll know exactly how to build your own ripple carry adder using VHDL and Vivado. Let's get started. Before we jump in, here's what you'll need. A computer, obviously. FPGA-related software. You can use any FPGA software, as long as it can build VHDL code and run simulations for your design. For this tutorial, we will use Vivado. If you want to use Vivado and don't know how to install it, you can go to my channel, find the related video. Third is some basic knowledge of digital logic and VHDL, but don't worry, I'll guide you through the entire process step by step. So, what exactly is a ripple carry adder? It's a simple yet fundamental circuit that allows us to add multi-bit binary numbers. By chaining together multiple full adders, we can perform multi-bit addition. Each adder computes a bit and passes its carry to the next stage, creating a ripple effect, hence the name ripple carry adder. The input of ripple carry adder includes 4 bits A, 4 bits B and a 1-bit C in. The output includes 4 bits sum and 1 bit C out. However, this design has a trade-off. The carry has to propagate, or ripple, through all the adders, which can result in delays as we increase the number of bits. Although it's not the fastest way to add numbers, but it's essential for understanding how multi-bit addition works in hardware. Before we dive into the hands-on part, let's quickly discuss where ripple carry adders are commonly used. They're a fundamental component in many digital systems, especially in arithmetic logic units, ALUs, inside CPUs, where fast addition of binary numbers is crucial. You'll also find them in digital signal processing, DSP, applications, calculators, and even hardware accelerator, where performance and efficiency are key. Though ripple carry adders are relatively simple, they form the building blocks for more advanced arithmetic circuits, making them essential for anyone learning about digital design. Now, in this tutorial, we'll go step by step to design a 4-bit ripple carry adder using VHDL. First, let's open Vivado and create a new project. Name the project something like ripple_carry_adder. In the past 2 lessons, we've covered the basics of VHDL and how to design simple circuits like the half adder and full adder. I hope you've been following along and are now familiar with the design flow. Now, there's one major difference in this design process compared to what we've done before. When creating the VHDL file for the ripple carry adder, we'll set the inputs and outputs to be bus types since we're dealing with 4-bit numbers. This means that the most significant bit, MSB, will be 3, and the least significant bit, LSB, will be 0. For the output, we want to combine C out and sum into one single value, so we'll define it as a 5-bit signal. In addition to creating a new VHDL file, we'll also be using the full adder we designed in the previous lesson. So, we'll add the full adder design file to our source by clicking Add Source, then Add File, and selecting the full adder file. Once that's done, the ripple carry adder VHDL file will automatically generate the multi-bit variables as vectors, which means the signal is multi-bit. In VHDL, a vector is simply a way of representing multiple bits in one signal. It's like having a collection of bits bundled together, where each bit can be accessed individually by indexing it with parentheses. Now, we move to the architecture where we describe the hardware structure. Next, we'll define two intermediate signals, which will represent the carry signals inside the ripple carry adder. Since we're combining sum and cout into a single value, we'll define an additional sum signal to store the output from each full adder. Based on the diagram we reviewed earlier, we'll define the inputs and outputs for each full adder. For example, FA0 represents the first full adder, and will connect its input signal I_A to the first bit of the ripple carry adder's input, A0. We copy the ports from full adder design file to here, so that we won't make any mistake for the spelling. When dealing with multi-bit vector signals, we use parentheses to specify which bit we're referring to. We'll follow the same method to connect all the other signals according to the diagram. After setting up the first full adder, we'll simply copy and paste this setup for the remaining 3 full adders, ensuring that each bit's connection is properly established. As for the results, we need to combine the cout with sum. Cout is the third bit of the value carry, we need to add it to the front of the sum. So a simple add equation can finish it. Once the circuit design is complete, we'll create a test bench to simulate and test the circuit. However, we encounter a syntax error, which we'll go back and fix later. Now let's build the test bench, as we have done in previous tutorials. For the test bench, we first define the input and output signals for the ripple carry adder. Just like in previous lessons, we'll use register-type signals for the inputs and wire-type signals for the outputs. Then, we define a UUT, unit under test, to represent the ripple carry adder we just designed, and we'll map the input and output signals accordingly. Next, inside the process block, we define a series of test cases to check if the circuit performs basic addition operations correctly. In 4-bit binary, each bit represents a power of 2, that is 8, 4, 2, 1. We'll mark the combinations we're testing with comments for easy comparison later on. At here, for 1-bit values, like Cn, we use single quote to mark them. But for multi-bit vectors, like A and B, their values are marked with double quotes. After completing the design, we run the simulation to see the results. First, let's set the simulation time to 60 nanoseconds by clicking the setting button. However, we get an error. So, we go back to the design file, and we find that there's an extra comma in the code. We'll remove the commas for each unit, and now the simulation runs without issues. Let's zoom in on the results. To make the addition clearer, we'll go to the value column on the left. The default format is hexadecimal, which isn't as intuitive for us. We can right-click the values, select radix, and choose Unsigned Decimal to view the numbers as we normally use them. We'll also hold Control to select all relevant variables and switch them to Unsigned Decimal. Now we can see that each combination produces the correct addition result. Additionally, we can change the format to binary to match the way we wrote the test bench, and by comparing it to the original diagram, we can clearly see that each bit behaves exactly as expected according to the full adder logic. So, the design is complete. However, we can still improve this circuit. After completing your own ripple carry adder, I encourage you to combine the clock writing methods we introduced in previous lessons to simulate multiple input combinations for A and B in the test bench. Instead of manually testing each combination, automate the process. For now, we've only tested cases where Cn equals 0. But what happens when Cn equals 1? How much bigger will the final results be compared to when Cn equals 0? Leave your answers in the comments, and let's discuss it. Lastly, I'll leave you with one final question. When designing the ripple carry adder, we manually defined the signal connections for each of the 4 full adders. But is there a more efficient way to simplify this process? Imagine you needed to design a 16-bit, 32-bit, or even a 128-bit adder. Manually defining each signal would be extremely inefficient. In the next lesson, I'll introduce a more efficient solution, but I encourage you to try it yourself first. Here's a hint: for loops and generate. That's all for today. Practice makes perfect, so keep experimenting and soon you'll become FPGA experts. If you found this lesson helpful, make sure to give it a thumbs up and subscribe to the channel for more VHDL tutorials. And if you have any questions or suggestions, feel free to leave a comment below. Thanks for watching, and I'll see you in the next video.